It's just Li. Yeah. Close enough, right?
Okay. Try to print it though, so that clear enough.
Actually, what's the time constant? I guess I'm still confused by this problem.
It's just inductors in general, I guess.
Inductors.
Yeah. I mean, I did the problem, but having to explain would be nice too.
Alright, you want this one?
That'd be nice. And this one probably not gonna really know how to do. I'm not looking forward. Actually, no, number 5.
So, you remember the resonant frequencies?
Yeah, I got that.
Okay, you remember what it is?
What is exactly?
Yeah.
Not really.
So the resonant frequency tells you about, I think you'll go over more of this. So we have, this can be basically, it's just these two registers.
It's like the energy that goes back and forth from the inductor to the capacitor.
Yeah, and the resonant frequency tells you the frequency of that energy. Okay. So you can use that resonant frequency to find out what's going on at the time. So let me see.
For the frequency? Because I have that written down.
No, for there's one that sine.
Q equals 2 mass
When it's
sine.
damping, though. This is RLC when it's damping. So it's not damping. Actually, you can use another two. Something like that. You can also relate it with the current. So it's either the current in the circuit, the resonant frequency, omega 2 plus 5, or Q max cosine omega 2 plus 5. So the only problem here, so they basically tell you that this is how the current is going to change. Current changes as Q changes. One is going to be a cosine function, one's going to be a sine, or they're both going to be cosine that sine, but with different phi. So all you have to do is figure out that phi and that function. So, I mean,
For number 4? Number 5?
yeah, for that number 5. So you have resistor, was it, or something? Battery.
Yes.
And switch, or something like that. And and your RLC circuit, you charge it, right? You charge it after a long time. How big is it? So this is going to be open circuit, short circuit. Open circuited, sorry. This is going to be open circuited, and this is going to be short circuited. Basically,
It's a wire, yeah.
Yeah, and so this is going to be charged with a Q, and this is going to be charged with current, right? And the positive negative, and this is going to have current want to flow this way. So current's going to flow this way, then it's going to flow back
back that way, it's going to flow back this way, it's going to flow back that way. And at the same time, it's going to be charged positively when the current flows this way at the end. So, I mean, this is why it's given as a sine or and a cosine. Let me just draw these graphs. Like, this is why one of them will be like that. So, let's assume that the current starts out 0. No, let's not assume that. Let's assume the current starts out at max.
Do we know that, or is it an assumption?
No, this is just not yet. It's just an assumption. So you want to figure out what the current starts out at and what the charge starts out at. But let's assume it's not this circuit, another circuit. Let's assume this is what happens in another circuit, right? That this is I. So I starts out at max, right?
Yeah.
I starts out at max. After a moment, I goes to 0. When I goes to 0, this is going to be charged. So I is going to be 0. This is going to be at its max, right? Positive max. So if you want to assume this is positive, this is negative, it's going to be negatively max because all the charge is going in that direction. So this is going to be negatively charged max. So I mean, positive flow. We are assuming current is positive flow. So positive flow charges this positively, right?
Yeah.
Which is the opposite of what we assumed it was. So this is going to be negative plus the opposite. So this is just a sign convention, right? And that's when the current is 0. After that, this is going to be creating the current because it's going to be discharging through the inductor. So the current through the inductor is going to be negative, and that's what this charge is going to be decreasing. Just here, close to positive, and this is back to 0, and etc. So this would correspond to this, and this would correspond to this. So in your situation, I believe both of them are charged at t equals 0, right?
That problem. I don't remember actually.
T equals 0, yeah, both of them should be charged because...
Yeah, because it's not at max,
Right. So both of them should be charged at, in that case.
Anytime it's 3.53 milliseconds.
By what?
3.53 milliseconds at that time. They were at that time.
You mean?
Oh no, that's the time after. Never mind.
Which one? What is Q1? Which one? Like I said.
I have this equation, and the homework is to use this to find a maximum somehow.
Yeah. So Qmax would be 155 microcoulombs. Maximum charge on the capacitor after the switch is open. Okay, you know how to find that, right? With the energy, right?
I did it this way, is that correct?
Okay. So one way you can do it is, wait, you did what, you said?
I got Q equals Q max.
Sine omega t, yeah, but you have a factor of phi. So let's say you want to describe, because you know that I is equal to dq over dt, so if you know your q of t, you're going to know your I of t, it's just the derivative of that.
Yeah.
So if you use your Qmax, if you want to use sine omega t, you don't have to use sine omega t, you can also use sine omega t. I mean, it has to be phi though. Sine omega t or cosine omega t plus phi. Phi tells you how much that function is shifted, as in where does it start.
Mm-hmm.
So your Qmax, do you remember how you found your Qmax?
Q max.
Yeah.
Q max equals I max over the omega frequency. Is that right? Somehow that worked.
Really?
Yeah.
I don't know.
I got help that way and that worked out.
Yeah, but I mean, you can also find it in a more rigid way. Do you have problems with these, Matthew?
Which ones?
RLC circuits.
There were only some questions that gave me issues. I knew the
Is
one.
this one? Is this the one? This is the same one.
This is RL.
It is the same reason. I'm doing LCD.
Oh, so.
Did you do the last one?
No,
Not yet.
no.
Okay. I'm not going to finish with the first. Joe, what's the one you're having an issue with?
The last part of the first one.
Okay. You're having an issue with the time constant?
I found the time constant
Okay.
based on what you said, but now I'm kind of unsure as to what to do with that equation for the current.
What? Wait. What are they asking for?
The current
Current
That
at a
was
certain
current
time.
down here at
Okay.
a certain time, you know?
Okay. You know your IMAX? This is IMAX. You
Open
open
time
the
now.
IMAX. The IMAX is the current right after it switches. Right?
No.
No?
No.
So it's going to start charging when you open the switch. It's going to start discharging. So it's going up, then it's going to go down.
Mm-hmm.
When's the maximum?
Right when you open
Yeah,
it?
right when you open it. That's when it's going to stop increasing, start decreasing.
You can probably continue with that.
You could do like energy conservations, right?
Yeah,
So like
that's
energy
what I was
factor
talking about.
equals.
Exactly. So, you know, in your circuit, you know, let me start a bit more deeply. So I'm going to put one inductor because you can simply put them in series, right? Because two
Yes.
inductors in series, you can sum them up. And get one inductor. So, okay. So, now, after a long time, you know what to calculate. You know how to calculate this, which is, it's not your IMAX actually in this situation. I'm going to call it I infinity. And you know how to calculate your Q infinity, right?
I believe so.
That's
Yeah.
after a long time. So all switch is open, and then right after as switch is closed, sorry, for a lifetime, this is your I infinity, sorry. So that's going to be your I infinity, and that's going to be your Q infinity, right? So it's going to be positive and negative in the direction of the current is this way. Because, so positive current flows like this, and stores positive charge here. Positive current is going like this. So right after it's open, one's going to have tendency to push in that direction, the other's going to have in that direction. It's going to push like that, and the other's going to push like that. Do you know what I mean?
Yeah, makes sense. Goes in reverse right after.
Okay, so when you open the switch, right? You open the switch, this is equal to Q0, so we're just basically shifting the time axis. So before it was infinity as with respect to opening having the switch closed, and this is 0 with respect to opening the switch. It's just a convention to, name them because it's easier to think of a time t equals 0 when the switch is opened.
Yeah.
Okay, so these are going to be your Q and I. Now, since there is no resistor, there's no external power source here, all the energy in it is going to be conserved, right?
Yeah.
So after a long time, the entire energy in the circuit, we forgot about this. This is disconnected. This entire circuit is disconnected. This entire circuit is disconnected. Why? Whatever. This entire circuit is disconnected. Now, so all the energy in the circuit is going to stay in the circuit, right?
Yeah.
So if you want to find your Qmax, the easiest, I guess the easiest way to do it is in the frequency. There's a formula for it. I don't remember if there was or not, but since you said there was, then so at any moment there may be. So since they're both given, one is given with a sine wave, the other is basically a cosine wave. There may be moments where there is charge, but there is no, this should correspond to the same time moment. There is charge, there is no current, or there is charge and current, or there is current and there is no charge. This corresponds to that, right? So, if you want to find the maximum possible charge that ever exists in the circuit, it's going to be, so the sum of energies, since CB, Q squared over
Q squared over C.
Q squared over C plus 1 over 2 Li squared. Right. So at any moment, this is the maximum energy. At any moment, this is the maximum energy.
Because you sum them together.
This is the total energy, sorry. This is the total energy stored inside. So the maximum charge is going to happen when there's no current in the circuit. When all that current is turned into charge stored in the capacitor. So that's going to equal 1 over 2 Q max squared over C. Right?
Yeah.
So this is, at any moment, this is constant, is equal to K. At any moment. When there's no this, all of this is K. When there's none of this, when there's no charge, this is going to be your K. So that's going to be your max. You know what I mean? It's the same calculation as potential energy and kinetic energy. This is when you have no kinetic energy, that's when the maximum potential energy exists, and there's no potential, etc. Now, when you calculate, you know your Qmax for your function, because we said we want to write it as Qt equals Qmax sine omega t plus phi. Right?
If you do cosine, you only need 5, right?
No, you.
It depends on the situation.
It depends on the situation. I mean, it's always, I mean, you most of the time you will need phi unless one starts at 0 and the other doesn't. Because here it's not going to be a cosine or a sine. It is going to be a cosine or sine, but it's going to be shifted by a certain degree, and you're going to have to determine that one. Because look, so you got your Qmax, right?
Yeah.
And you know that Q0 is equal to Q0 that you found, right?
Mm-hmm.
Equal to.
Let me go back to the problem. Q0. Did I find that?
You didn't find it?
What do you need Q0? Like it just right after.
How'd you find this?
Number 4?
Yeah.
I just plug everything in, and then Q is that answer. Because we have Q max, we have time, and we know what omega is.
Q is equal to Q max sine omega t. So that's a function of Q. What's that your function of Q? Is t equals 0 in the switch only?
Yeah, t equals 0 when the switch is open.
When the switch is open, okay. What is as far as I know, sine of 0 is
Sine
Zero.
of 0 is 0. Yes.
so Q of 0 is 0. But Q of 0 in this situation is it's going to be 0. Yeah.
It's all good?
Yeah, the capacitor is going to discharge. I misled you, sorry. So there was a resistor that would discharge, and there would have to be a voltage across the capacitor's plate, and therefore a charge. Because if you remember the only thing about a resistor here, right?
Resistor damping, right?
Yeah, it's not about damping in this situation. It's about this is the only thing class, right? And you found out that the capacitor has charge eventually, and not 0 charge at the beginning.
Yeah. I think so.
Because so after a long time, the inductor is going to be a wire, basically, right?
Yeah.
And there's going to be voltage across here. That means there's going to be a voltage across here. That means there must be charge across the capacitor.
And
But
they're the same.
Yeah, the same voltage. But in this situation, after a long time, this becomes a wire. That means the voltage across here has to be 0, since it's a wire. And that means the voltage across the capacitor has to be 0. That's why it has no charge. So in this situation, yeah, you don't even need this entire. So yeah, you basically your thing, your phi is going to be 0.
Okay. How do we determine that it's 0?
I really want to go over this because I really feel like I misled you, so I'd rather just continue a bit with this. I just added this resistor here, R, alright?
Okay.
Because this is what's going to change the situation. Because, so, as I was saying, let me do this. Why?
Maybe you need like a small eraser.
So, if you had no resistor here, after infinite amount of time or whatever, this is all going to be a wire, right? So the voltage across any wire is always zero, by assumption, by convention, I guess. So the voltage from here to here is zero. The voltage from here to here is zero. And since C equals Q over V, Q has to be zero for V to be zero, right?
Mm-hmm.
C equals Q has to be zero. If there was a resistor here, after a long time, this still becomes a wire, but the voltage across the resistor exists because there's current flowing through the circuit. Therefore, there is a voltage here.
And they're the same, right? Still.
The voltage across here is going to be the same as the voltage across here. So that's when you find your Q. That's your Q infinity or Q0. That's your Q which you move with from before switches open to after switches open.
That's Q0, right?
That's Q0, yeah, Q0. And it's going to have a value. It's not going to be Q0. It's not going to be zero in this situation. It's not going to be equal to. Sorry, it's not going to be equal to zero in this situation. It's going to have a value because
right.
Yeah. So it's going to have a value. And you can use Q0, you're going to know that value because you know how to calculate it from before the circuit. Basically, it's just a regular circuit. You have to find the voltage. You know the current, find the current through the resistor, and V equals IR gives you the voltage across here, which will give you the voltage across here. C equals Q over V will give you the voltage and will give you Q. So that's your Q0. This is going to be your Q0. What does this equation tell you? Q0, and you already found this from energy, like we said. You're going to have no Q, no I. So you shouldn't have a problem finding Q0 and I0 after it's open. Q0 and I0 should be the easiest things to find.
Yeah, they are.
Because before the circuit, before you open the switch, the circuit's basically a regular circuit which you can analyze by voltage, division, resistor, finding equivalent resistance and whatever, and that. So you should have your Q0 and I0. With that Q0 and I0, you find your Qmax, and you put it in this equation, Qmax. So you know your Q0 is equal to Qmax sine omega t, 0, because you're talking about T0, plus phi, right?
Mm-hmm.
And this is equal to the Q0 that you found. It's going to be a number, right? You know your Qmax, you divide by that. Sine phi is equal to that. That's how you find your phi.
Can you repeat that again?
Okay. You know your Qmax, right?
Yeah.
Found it. You know the number, which is Q0. That's going to be Q0. Because we just put a number to show that it's unknown, right?
Mm-hmm.
So that's going to be sine 0 plus phi is phi. It's equal to that number, Q0 over Qmax.
So
And
that's
that's
what
sine,
phi.
that gives you phi. And that's how much it's going to be switched. In the situation like this, your Q0 is going to be 0, that's why your phi is going to be 0.
Okay.
Right? Yes. And since since we found a function of, like you did, you already found a function of, so back to your situation, Q T is equal to Q max sine omega t, I of t is equal to dq over dt, which is equal to Q max omega cosine omega t. Right? Derivative
Mm-hmm.
with respect to t.
So.
And yeah, okay, this is why it's IMAX. IMAX is
That's IMAX, right?
Omega. Right.
Okay. So that's why it worked out, right?
That's why it works out, right? Yeah.
And knowing phi, then we could find the maximum value
You know
for
what?
number 5.
Yeah, with that equation, yeah, you can find the maximum value. That's it.
That clear we don't know this part.
Oh, you're doing this one? Oh.
Mm-hmm. Section 1.
Okay. I was just trying to close for a very long time. milliseconds after the switch is open. Okay, what'd you do?
First, got the time constant.
Right.
It's because when,
Yeah, because
like you said, when the
right.
switch is open, you ignore this.
Mhm. Okay.
And then I
Sequence of
did
the
trying
time.
several things.
What'd you do? I3. What's the equation for I3?
Oh, no.
What's the
The
equation for
equation
I?
for-
I mean, yeah, I of t to okay. If you over R, you can make it t over tau.
Mhm.
All right. What's your I max? What's your v over R? I mean?
I assume that is the current through the circuit without the inductor, and then inductor acting as a wire.
Yeah, it's the current through the inductor.
So then it's this number.
So the current here.
Wait, it's the current through the inductor?
Yeah, because that's what we're talking about. The current. This is I max of the inductor, not the circuit. Because the inductor stores that.
No.
I mean, there is no reason to talk about anything else right now.
Mm-hmm.
So that's your. Is that your? Is this I4?
Is what?
Oh,
Or is that
No.
IL? So you need to find that.
Yeah, I
You
need
need
to
to find
find
I.
Yeah, one last question. Suppose problem 2. They ask you for Q1. Yeah. And I did like energy conservation, and I equated the energy of the inductor to the energy of the capacitor.
Q1 is the max, and I put the maximum charge on the capacitor.
Okay.
Well, how does that work out?
What'd you do?
I equated the energy of the inductor to the energy of the capacitor. And doing that, I guess solve for charge. Q max.
You know the initial charges on them, or what do you know what circuit?
Those the capacitor, so when the inductor is at time t equals 0, the current through the inductor is maximum value, and it has a current control.
Okay. Now, remember capacitors and stuff in series?
Capacitor
Capacitors
series?
in series, yeah.
Yeah.
So the charge on a capacitor and two capacitors. You want to turn them into one capacitor in series. What do you know about the charge? This is Q1, this is Q2.
I know you can add them up first. I know you can add them up first.
And
And then
what?
charge equals
Okay,
capacitance times voltage, right?
what's Q equal to?
Capacitance times voltage. Q to CV, right?
So this is going to be Q is equal to CV, right?
Yeah.
And we know that C for two capacitors in series, 1 over C1 is 1 over C2, right?
Yeah.
So that's going to be equal to 1 over C1 plus 1 over C2 times V. This is your V. This minus V. And so this is going to be here. Plus minus V. So let's put each one into. This is a V2 plus minus. And this is plus minus V1. Right? So V is just going to be the sum of V1 plus V2. We want to do it with current. Actually, it's easier to do it with voltage. V equals let's see if we can do it that way. No. Okay, yeah, it works that way, I guess. I'm just trying to get to that they're both in series. Yeah, when they're in series, you add the Q is the same. But I realized I did it the long way, and there's a way easier way that I should have done. I don't know if I want to do that. Well, they're both in. If you don't remember, yeah, I can. Okay, we can derive it. But let me derive it the right way with the process. Sorry. You derive it with voltages, not with charge. You derive it that when you have these two in series and you want to.
Oh, you know, if you draw like a circle and you tap the center of the circle, it just gives you something. If you draw like a whole circle.
Oh yeah, it does. I forget. Yeah, it does. Yeah, someone told me. I was amazed. So this is going to be, again, this is going to be your V in that situation. This is your C. This is your C1. This is your C2. This is going to be V2. The cross is going to be V1. So going to tell you that V is equal to V1 plus V2. So V is equal to charge. This is V is equal to, what's V? This C equals Q over V. V is equal to Q over C. Q over C is equal to Q1 over C1 plus Q2 over C2. Good?
Mm-hmm.
But where's this not working out? Okay. So each one is that much charge on each plate.
Is charge supposed to be the same?
Yeah,
For
the
series?
series is the same.
And in parallel, and are they the
The
same
charge
too?
is going to be distributed, yeah. But yeah, the charge is supposed to be the same
For series or
for series.
and in parallel you add them, right?
And in parallel, yeah, you add the two charges on each one. Because it's like, so basically when you, it's analogous to, what's it called, current resistors, currents and resistors. It's going to be the same, whatever.
Okay.
And also you can think about it as induction. So when something here induces a charge, positive charge here, this is going to induce that same positive charge here. But the negative charge is going to jump from this side to this side. Oh. That's just the details. So yeah, I mean, if you put a charge here, that same charge is going to be negative here, right?
Yeah.
And that's going to flow here, right? And induce so the positive charges are going to run from here to here. And this is going to induce a negative charge, which so the positive charges run from here to here. So it's like a gate that nothing more than this can flow from here to here.
Mm-hmm.
So the charge is going to be the same. Basically, charge here. So if you have two capacitors, inductor, is there a resistor?
Any problem?
Yeah.
No, there wasn't.
No?
No.
Okay, so you can basically sum these up to one capacitor, C. Your equivalent capacitance is 1 over C1, 1 over C, 1 over C1, or you can do just 1 over C1 plus 1 over C2, or C is equal to C1, C2, C1 plus C2. This is basically simplifying this. That's your C equivalent C. And this C has a certain Q. Put T first, function of time. And this is inductor L, has a certain I of T, also a function of time. And we want it to Q max.
Yes.
So, okay, so you know that at T equals 0, I is equal to max. Right? Is it?
Should it be equal to max or
Is that what they asked for? Is that what they told you in the question? I don't remember the problem. I think it's 0.
for inductor is
It's an inductor.
Yeah.
Inductor. The depends where the inductor has its maximum value. Yeah. So I is max.
at T equals 0.
At T equals 0. That means Q equals. So Q is, what's Q at T equals 0?
It'll be 0.
Right. Let's say it'll be 0. So when I is equal to 0, Q should be max. But do you really need to, they don't ask you about any time?
For number 2, ask you at 21 milliseconds.
Okay, 21 milliseconds. So
You wanna
yeah,
find the
you need to
charge.
find the equation for it, yeah.
So I just like equated energies of those two, and
Oh yeah, that works. Yeah.
that's fine.
Yeah,
Even though
because
at the
hey, you're
times-
using IMAX here, though, right?
Yes.
Yeah, if you're using IMAX, yeah, because I mean, originally the entire equation would be 1/2. So at any time, 1/2 q is 1/2 q squared over c plus 1/2 li squared equal to k. So q squared over c is 0 max, and this is max. Since you're using this maximum value, you can use this 0 value, which is equal to.
So okay. So that's handy. So could I have done the same method for this problem too, or no? Like if I want to find charge.
This is the one that we're. No,
That's what we did earlier.
Okay, what is it? What's the one?
It's the same method using the potential energy of the inductor and equating it to capacitor.
If this is open here, if this is not here, I mean, yeah. So I mean, don't think about it as equating because that might. So you might not have a maximum value.
If it's not given to us,
If it's not maximum value, it's not going to work out. I mean,
Yeah.
at any time, it's just that you want U energy. Is that what they use energy? U is for energy. U.
potential.
That's potential. Symbols. W.
We use
E.
like E.
E.
Yeah.
E. Okay. E. E capacitor plus E inductor is equal to K at any time constant. Or is C a constant? I guess C is a constant. Or C is a capacitance. No, it's K.
K works.
K works. K. Alright. E C plus E L is equal to K at any time, right? Now, these should be at, like, since they're a function of T, right? Function of T. This should be the same T. So if you're doing it when this is max, this has to be 0. So if this is E of C at TQ max, that's the time when Q is maximum, plus E of L has to be at the same time, T of max. So since this is maximum, this is 0.
That'd be 0. Yeah.
This is going to be Q max. Yeah. And you can equate them if only they're maximum.
Okay.
If one of them is the maximum, you want to find the maximum of the other.
That's the one.
Because the other one's going to be 0.
Yeah. Makes sense then. Ready? You go home and have dinner.
You done?
So,
Okay.
just for now.
What's up?
No progress. Just started doing the next lecture.
What do you think happened?
I don't understand the formula anymore. So this is the maximum
IMAX,
current
yeah.
through the circuit or the inductor?
The inductor.
Okay, then what is this current? The current
Inductor.
through the inductor
Yeah.
at any point?
At any time. Okay.
Okay. I got the IMAX from
Yeah.
the all current, and I'm getting the specific branch going through the inductor.
Okay. Did you do that? Did you get it? You said?
Yeah,
Okay.
IL down here. So that would be the IMAX, I believe.
Yeah. If that's I infinity, then yeah, that's IMAX.
And then I tried plugging it in. I got a current of 10.
Okay. How'd you do this?
How did I do it?
Yeah. How'd you do this?
How did I get the current?
Yeah. How'd you do? How'd you get the current?
I got the current from treating the inductor like a wire. So
Okay. So these
then
are
you add
parallel.
up these resistors in parallel, series,
Right.
and then 12 over that gets you the current of all.
Here, right?
Yeah, and then you do the all current, and you do, what is it, 65 over 40 plus 65 times all the current, and that's your current
That's your
through this
branch,
branch. And that should be IL.
Right. That's right. So that's your IL. Right. And your, I think, okay, I think I know your problem because I ran into the same one. So, why is it 10? I think you used the one. Did you use the wrong units?
I would assume not.
What is this?
That's amps.
That's amps. These are in ohms.
Yeah.
This is in microhenries.
Yep.
And millihenries, sorry.
Oh,
Okay, this is.
Is this? No, this isn't.
Okay. Sure. Everything is right because 10 amps is kind of a lot.
It is.
Especially that your max, I max is smaller
That's kind of concerning.
than it. Yeah, it is. So, you want it after 6.8 milliseconds, and your tau is in 0.37. So that's 0.37 millihenries, right? Over ohms, that's going to be in 0.3 milliseconds. No, that should be right actually. Weird. 6.8 0. These units. They're good. They like you.
I am. Oh, for
Is this the
S.
same?
Cursive S. Because I would use mix and multiply if I use a print one.
It's 0.375. Oh yeah, this is in milliseconds. This should be in milliseconds.
How's it?
Because this is millimeters.
0.375 is in Henry's.
How much did you do that? Okay, then you didn't convert. Okay, what's your T or tau? That means I of T is equal to 0.037563 times e to the negative T. T over tau, which is 0.003571, where T is equal to, what's T?
T. Oh, 0.0068 seconds.
Huh. Oh, you didn't do T over tau.
This is over tau, isn't it?
T divided by tau.
Oh, what the heck?
Yeah.
Oh, I dropped the parentheses. Sorry. Are you serious? That better not be the reason. I was missing parentheses, so I interpreted it differently.
That's why you want that. Oh yeah, it's just so what direction is it going? Yeah, look back at the graph. They tell you this is positive. And what direction is it going?
I'm confused. How would you be able to tell? They tell you this is positive. How do you know it's going this way?
They tell you I3. They're asking about I3.
Oh, I3. So their direction is incorrect.
Their direction is positive. I mean, no, but it's not incorrect. But I mean, they're assuming they're putting that to the positive direction of current. So it may be different.
Oh, so when it goes across R3, it's negative.
So if the current flows in this direction, then the current is positive. If the current flows in that direction, then it's negative.
Why is it flowing in this direction?
Why? Because before when the switch is closed, you have current flowing like this, right?
Mm-hmm.
Right.
Yeah.
Now the current keeps on flowing like this, and the inductor stores. It kind of like stores current.
This will do that backwards thingy.
So the inductor stores current in that direction.
Mm-hmm.
Right? And when it stops, when it stops charging or whatever, the circuit, it keeps the current flowing in that direction. It doesn't flip the current or anything. Now, if you're confused about that, why? Is that what you're confused about? Why? Or what?
No, if it keeps the same direction,
Yeah.
isn't this?
No, it keeps it in the inductor. We're only looking at the inductor. The inductor is the one storing energy, so it is the one that determines which direction the current goes.
Mm-hmm.
So if the current before the inductor is going downward, it's going to keep on going downward after you open the switch. So the inductor is going to keep on going downward.
Oh,
and since
okay.
this is your circuit, now this is going to be flipped. So you're going that direction now. The inductor current is the same direction. Before it was in this direction, now it's in this direction. But since this is what changed, now it's only this circuit. Before it was like this.
Mm-hmm.
These two are going downward. And now it's like this. This
It's going in the same direction. Oh.
Yeah, this direction is the same, but this is the one that flipped. Before it was going downward.
Oh, okay.
Now
I
it's
get
showing
you.
this is going upward.
When it's just closed, that's when the voltage is at the maximum, right? And then when it's been open for a long time, it's zero.
When it's open for
Oh wait, no, that doesn't make any sense.
when it's closed.
Just the current does that.
For now, do it when it's closed.
Would that be? Wait, when it's just closed, it acts like an open circuit, doesn't it?
Mm-hmm.
So this gets cut off.
Mm-hmm.
So whatever current is going through here.
Mm-hmm.
So is it just the all current? No.
That all current you calculated with this resistor. But when it's just closed, you don't really care about this.
Oh, so just the left side.
The left side, yeah.
So 12 divided by 40 plus 60. Is there voltage across an inductor when the circuit is open?
Is there voltage across the inductor when the circuit is open?
Yeah, it says when.
What's the maximum voltage range?
I don't get the maximum. I thought would be 0.
Isn't that what they want?
Yeah.
What is the maximum voltage across the inductor when the circuit is open? Okay, what's the voltage of the inductor?
The voltage of it.
Mm-hmm.
How would you determine that?
Ah.
Oh. It would be discharging current when it's open.
It would be discharging current, right? I think they want the magnitude, so it's going to be negative since it's discharging. So it's negative, it's going to be negative, but I think they need the magnitude.
Mm-hmm.
Or since Imax is flowing this direction, right when you open it, right?
Mm-hmm.
When you open it, its maximum is going to start decreasing. Right when you open it, this is all Imax going that direction, right?
Mm-hmm.
Right? So, since across A, sorry, it's going to be opposite. It's going to be negative. It's going to be positive. Since V is equal to I, R.
That thing's going to act like your battery?
No, it's not going to act like a battery, but the voltage across the resistor is equal to the voltage across the inductor. Because they're in parallel in series, but I mean, it's not really in parallel, actually, but it's going to be negative voltage, because all the voltage that the inductor supplies, it's going to be lost across the resistor, right? So the voltage here is going to be equal to the voltage here.
So Imax being what we just found before it was opened?
Yeah, the maximum, yeah. Imax is what we just found, the max, which is I infinity before it was open.
The same value that was used in the last part of the IL? Okay.
That's your reference.
and it occurs at that moment, and so the voltage across the inductor is always going to be negative the voltage across the resistor, because all the voltage that this supplies is lost across the resistor. Because they're the only two elements, so it's like a battery and a resistor.
This might sound stupid, but is there any point at which the voltage is zero in the inductor?
Yeah, there's no current through the inductor. There's a current through the circuit zero, there's a current through the resistor zero.
But that's not always true, because when the circuit is first closed,
When the circuit is first closed.
yeah, the inductor resists current at
Yeah.
that instant.
Yeah.
But there can still be a voltage traveling across there.
There's a voltage across it, but it's an open circuit. Okay, so what's the graph of current in the inductor? This is
It starts at zero.
when it's closed. Closed at t equals 0, right?
Mhm.
Starts at 0. Right?
Yeah.
This is I. Are you convinced of this?
Mhm.
Okay. After you open it, opened, so you will here,
That goes back down.
right?
Mhm.
Okay. So, since we said V equals L di dt, right?
Yeah.
V is equal to 0 when di dt equals 0. V is equal to max when di dt is equal to max. Di dt is the rate of change. When's the rate of change maximum here?
At zero.
The slope is the maximum. When the slope starts to decrease. Here, the voltage is maximum.
Mhm.
Here, the voltage is 0 because di dt, well, not 0, approximately. It never really reaches 0.
Physically, it can be zero.
Physically, it can be 0. Theoretically, it can be 0. Because, I mean, so after 4 time constants, after 4 amount of taus, the current is going to be, after 5 taus actually, the current is going to be 0.006% of its original value, which is absolutely nothing. 0.006%.
Mhm.
That's really small. So you can basically ignore it after 4 or 5 time constants. And the same thing here. Maximum voltage here, voltage drops 0 after it's open. That's the maximum voltage. It has to drop. Because the slope is changing.
That's an easy way to think about
And remember that the voltage doesn't have to be continuous, so the voltage can jump
it. Mhm.
because that's not resistor. Because I mean, the current's job, the inductor's job is to keep the current flowing the same way it was before. With the same value, same initial value.
Yeah.
So initially it was like this. So it started like that, right?
Mhm.
First, before the circuit was even closed, no current was flowing, right? Initially, like long time ago.
Mhm.
Like, long time ago.
Just charged, nothing going on.
Nothing was going on, right? Nothing was going on before it was closed, right?
Mhm.
Now, it was closed. The inductor doesn't want to change immediately.
Mhm.
It has to change slowly. So it's here, it's trying to keep it 0 because before it was 0,
Yeah.
right? But the battery slowly wins out, right?
Mhm.
The battery slowly charges it, and the current slowly increases. Here, we take the battery out, right?
Mhm.
And just law of physics, the physical laws of nature says that,
So it's just to prevent rapid changes.
yeah, it has to
And the
prevent
current?
That's what it wants to do. Yeah, it wants to prevent rapid changes in current. That's why it slowly pushes. It has to push something. So
Mhm.
that's why it's keeping it. And think about it this way too. So it has to prevent rapid change in the current, right?
Mhm.
That means the graph of I has to be continuous. Because as long as you don't have a jump in the graph, that means there are no rapid changes. So this change slowly, because all the graph is continuous. And since the graph is always continuous, V is going to have a value. If the graph is not continuous, the IDT is equal to infinity, V is equal to infinity. There's no such thing as infinite voltage. There can't be a jump.
It has to be so.
I don't know what formulas to apply for the second part of the homework. For one, I know the capacitors needed to be summed up for this question, but
Yeah.
okay, that's their equivalent capacitance. In terms of the charge formula, I guess you might be able to use potential energy on this one.
Yeah, yeah, energy, yeah, energy.